So today we're going to move on to something that I'm sure that you have repressed memories of, and that is finding real zeros of polynomial functions. And that is because this requires polynomial long division. And I know that most people dislike long division. Well, okay, so it doesn't require long division. Yeah, there's shortcuts. You could use synthetic division, which we will do. But it's not going to change the fact that this is a lengthy process. And that's okay. That's okay. We're all pretty smart here. Okay, so division, whether it's of numbers or polynomials, involves a dividend divided by a divisor, that's the academic vocabulary for you, to obtain a quotient and a remainder. This results in this kind of equation: divisor times quotient plus remainder equals dividend. The good news is I am not going to quiz you on that stuff. You will not be assessed on that kind of verbiage. But you will be assessed on your ability to produce these things. I'm just not going to be like, hey, surprise, what's the dividend? What's the quotient? I'm not going to do that. So it says if f of x and, oh God, I'm falling. If f of x and d of x are polynomials of degree f greater than or equal to the degree of d, of course, the thing you're dividing by can't be 0. Then there are unique polynomials, q of x, quotient, and r of x, remainder, so that our function f of x can be written as the multiplication of several things plus a remainder. And that should make pretty much good sense to you. When you divide a polynomial by another polynomial, you end up with a polynomial, and then usually remainder, sometimes a remainder. And that's what that's saying right there. It's actually a lot easier than it looks. That's the good news. You know, of course, if you know how to do long division, that is. So it says use long division, yuck, but we got to use long division to find the quotient and the remainder when 2x to the fourth minus x to the third minus 2 is divided by that quadratic, and write a summary statement in both polynomial and fraction form. That's probably new, but don't stress, it's not hard, I promise. Okay. At least the ending stuff. Now, I won't say that it's a quick process. It's definitely not a quick process. What are we dividing? We are dividing a quartic by a quadratic. And let's see, 2x to the fourth minus x to the third. Okay, first thing I have to mention. When doing long division, you cannot have any missing terms. And what I mean by that is the thing underneath the division symbol, it can't have missing terms. And the thing you're dividing by, it shouldn't have missing terms. Mr. M, what are missing terms? Well, you know, if I were to write this polynomial in standard form, technically, it is supposed to count down from the power 4 all the way down to the power of 0. I happen to be missing the power of 2 and the power of 1, and that could cause us a problem. So yeah, we can't have any missing terms. Let's see. So after the x to the third, I do need to have an x squared term. Mr. M, I don't have an x squared term. I go, you are right. So why don't you call it 0x squared? And you also don't have an x to the first term. So call it 0x. Then you do have a minus 2. Cool. And let's see, draw my divisor. Whoa, 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 whoa. The pen squeaked. Sorry. Oh, God, that was awful. Okay. I have not left myself enough space, so just give me a momentito to fix that.
You won't give us one where like it's 1/2 x cubed, right?
Long division with fractions would just be mean, so no, I won't do that to you. Alrighty, now let's do the outside one. Okay, 2x squared plus x plus 1. Luckily, the thing we're dividing by that goes on the outside, it is not missing any terms, so we don't have to fill in any 0 terms for that one. So we have 2x squared plus x plus 1. Okay, now this is how this process works. Your job is to look at the front terms only. The front terms only. So this one on the outside is a 2x squared. The one on the inside is a 2x to the fourth. We need to multiply that 2x squared by something to make it be a 2x to the fourth. What would I need to multiply this by to get this? X squared, yes. So I need to multiply by x squared. That x squared will be written over here. And why did I put it there? Just because I want my like terms to line up. That's the only reason why I wrote it way over there. It doesn't matter if you write it closer to the front. Doesn't matter. Don't stress out about it. I just like my like terms to be stacked up and down. you're going to take that x squared and you're going to distribute it to the divisor on the outside. Distribute that x squared to the divisor on the outside. And I'm going to erase these lines so you don't write them, but you're distributing to all three of those positions. And when you do, you will get 2x to the fourth, woohoo, they match, plus x to the third, oh, look at this, like terms lining up perfectly, plus x squared. I have not left myself anywhere near enough space. I'm going to have to shrink what I wrote, but there it is. This is why you needed that 0x squared term. It's that your like terms would have lined up. Just like regular long division that you learned about way back in probably 4th or 5th grade. Your job here is to subtract and see what's left over. So let's go ahead and subtract straight down. See what we get. 2x to the fourth minus 2x to the fourth, 0. Fantastic. Watch your negative signs. Negative x to the third minus x to the third. Negative 2x to the third. 0x squared minus x squared. Negative x squared. And now you bring down the 0x. Awesome. Again, you're only paying attention to the front terms. Your job is make them match. I need this 2x squared to match this negative 2x to the third now. I have to multiply that 2x squared by something to get negative 2x to the third. What would I have to multiply 2x squared by to get negative 2x to the third? Negative x. See, my like terms are still lining up. Just like before, you're going to take the thing you just wrote and distribute it to the divisor on the outside. So that negative x is getting distributed to 2x squared plus x plus 1. And that's going to give me negative 2x to the third minus x squared minus x. And just like before, you will subtract straight down. I have not given myself anywhere near enough space, so I'm trying to remedy that. There we go. Now I have more space. Subtracting straight down, being very careful with my negatives and my double negatives and things like that. Negative 2x to the third minus negative 2x to the third. Minus negative means plus. So yeah, that gives me 0. Cool. Negative x squared minus negative x squared. Ooh, rare treat. More than one thing canceled out. Another 0. 0x minus negative x. That gives me positive x. And you would be dropping down that minus 2. And guess what? The degree on the bottom is less than the degree of the divisor. That means you're finished. You cannot divide any longer. The degree down here at x minus 2 is less than the degree over here at your divisor. Finito. So that is your remainder. So this is how you would write this. Let's first write it in, did I write it in polynomial form first? I did. Here's the polynomial form. Our f of x can be represented by, and hopefully I can fit this, or you know what, maybe I'll just shrink this again to make sure I have space. There we go. Yeah, now I have plenty of space. Shrink it again. I know that 2x squared plus x plus 1 times my result of x squared minus x plus the remainder of x minus 2. I know that if I do 2x squared plus x plus 1 times x squared minus x and I add x minus 2, I will get back this. So that is the polynomial statement. It just says, yo, if you want to get back your original f of x, you'd have to multiply your divisor and your dividend and add the remainder. And that would give you back the original function. That's what it looks like in polynomial form. Make it easier for you. Let's use numbers that you're comfortable with. If I said 12 divided by 5, okay, well, 5 goes into 12 2 times, right? 12 divided by 5 is 2 with a remainder of 2. So I can say 12 is equal to 5 times 2 plus 2. That's what we're doing, if that makes sense. We're just saying a statement. This is how you get back your original stuff. What you are used to seeing is this. You saw things like this in Algebra 2. 2x to the fourth minus x to the third minus 2 divided by 2x squared plus x plus 1 equals. x squared minus x plus the remainder of x minus 2 when I divided by 2x squared plus x plus 1. That's probably how you did it in Algebra 2 Honors. So the top one is a polynomial, and the bottom one is a fraction. Cool with this? If not, you got to say something to me. Nobody's saying anything. So does that mean everybody gets it? I'm a little worried about that.
Did you say the last one? I'm sorry, I didn't quite catch that. The one you just put up, was that in fraction form?
Yes, this one's polynomial form, and this one's fraction form.
Okay. Great.
Let me write, I used a numeric example a moment ago. 12 divided by 5 is equal to, it goes in 2 times, right? 2 times 5 plus the remainder of 2. That would be the polynomial form. Actually, what I should say, polynomial form would be 12 equals. Come on, active panel, catch up with me, please. Here we go. This is polynomial form. And this is poly. I'm just using a general term, 12. That's polynomial form. And fraction form would have looked like this. 12 divided by 5 is equal to 2 plus the remainder of 2/5. Those two statements say exactly the same thing. These say exactly the same thing. I'm legitimately sweating. This AC is broke, folks.
For the polynomial form, shouldn't it be 2x? Oh wait, never mind. I just got it.
You sure?
Yeah, I just got it.
Okay.
I think.
See, if you take that fraction form that I just wrote down there in red, and you distribute a 5 across the entire statement, you get 12 equals 2 times 5 plus 2. So they are exactly the same thing. Is it a question about the material or a question about the broken AC? I can't help the broken AC.
Is it going to be broken all day?
I have no clue. Nobody knows.
Like all building 4?
The entire building is broken right now. No AC in the building. Okay. Remainder theorem. Opening a window won't help. Remainder theorem. If a polynomial is divided by x minus k, then we say that the remainder is, well, f of k, which is actually really interesting. Okay, first of all, what we're saying here is if I divide a polynomial by a degree 1 binomial, like x plus 1 or something like that, has to be degree 1, specifically that is x plus or minus a number. It does not have an exponent on the x. The remainder will be a number every single time if a remainder exists. And the really neat thing about it is if you want to know what that remainder is, you could either go through the process of division or you could just evaluate f of k. You could plug in the 0 of the thing you're dividing by. So if I was going to divide a polynomial by x plus 2, and I'm just curious to know what the remainder is before I do any work, I go, well, let me plug in -2 and see what I get. And whatever number I get would be the remainder. It's just really interesting. And if you were to get a remainder of 0, that means you divided by one of that function's factors. For example, I divide 12 by 5. Did I get a remainder? Yes. That's because 5 is not a factor of 12. If I were to divide 12 by 3, would I get a remainder? No, that's because 3 is a factor of 12. Polynomials behave just like numbers. So it just says find the remainder when you divide. That doesn't mean divide, that's too much work. What that means is use the remainder theorem. So if I was going to divide, that's green. If I was going to divide f of x by x minus 2, I would get a remainder of f of 2, because 2 is the 0 of that factor of the divisor. So we just plug it into everywhere we had an x. And whatever number we get, that would have been the remainder. Let's see. This is going to be 3 times 4 plus 14 minus 20, or 12 plus 14 minus 20. What is that? 26 minus 26. There you go. If you were to have divided f of x by x minus 2, you would have gotten a remainder of 6. What does that tell you? That tells you that x minus 2 is not a factor of f of x. Question for me.
Can you get like an x in the remainder?
So we can't get an x in the remainder as long as we're dividing by a linear divisor. As long as this thing is degree 1, there will never be an x in the remainder. If it's degree 2 or higher, then there probably will be x's in the remainder, yes. But the remainder theorem only works when you're talking about linear divisors. Yes, sir? Yeah, go for it. You don't have to ask. Okay, let's do the same thing for part B. Part B. Can I scroll down any further, or is that it? I got a little bit more space. Not much. Let's just give myself a little bit more space. Part B says, what would be the remainder if you divided by x plus 1? Well, I don't feel like doing all that hard work, so I'm just going to use your remainder theorem, and instead I will plug in the 0 of x equals negative 1. And let's see what happens. Let's plug in negative 1 everywhere we had an x. Show a little bit less work. We can do this in our head. Negative 1 squared is 1. 3 minus 7 minus 20, that is negative 24. So the remainder, if we were to have divided by x plus 4, would have been negative 24. Again, what does that tell us? That tells us that x plus 1 was not a factor of f of x. That's what it tells us.
I'm sorry. Can we back up for a second? How would we know that that x plus 1 isn't a factor of it?
Well, if I do 12 divided by 5, I get a remainder, correct? Right? Well,
Right.
Since there's a remainder, it tells you 5 is not a factor of 12. The only way you've actually found a factor is if the remainder is 0. It's like 12 divided by 3 has a remainder of 0. So 3 is a factor of 12. By the way, the AC just turned back on if you can't hear it.
Yes. What if they turned on like the heater on accident?
Shrink this up so I've got some more space for part C. Part C. This time we're going to divide by x plus 4. Again, instead of doing the long division, if we're just looking for the remainder, we can evaluate the 0 so we can plug in negative 4 and see what we get. F of negative 4 got a negative 4 here, here, here. Let's see what we get. Again, trying to show less work here. Negative 4 squared is 16. 3 times 16 is 48. Minus 28 minus 20, that is 0. Guess what, folks? We found a factor of f of x.
You're saying if you were to divide by x plus 4, you would get 0?
That's what I'm saying. If you were to divide by x plus 4, you would get a remainder of 0. You would have found one of f of x's factors. So since, what I write? Since f of negative 4 equals 0, x plus 4 is a factor of f of x. So if you were to try to factor f of x, one of your results would be x plus 4. That means the other one would have to be 3x minus 5. Doesn't have a choice. More importantly, you know what else that tells us? That tells us that x equals negative 4 is one of the solutions, one of the x-intercepts of this graph. X equals negative 4 is an x-intercept for f of x. And that is power right there, folks. That's going to help us graph this function. We now know where one of its x-intercepts is. And that's the whole point of this. The whole point is trying to identify x-intercepts quickly and as efficiently as possible. That way we can graph polynomials of higher degree. Are we calm, cool, and collected on the remainder theorem and polynomial long division? Nobody's screaming in terror. My question for you is, who likes long division? Oh, an honest answer from the classroom. He says nobody. Well, your L was backwards. How are you going to call me a loser and your L was backwards? All right, so we're going to... He only has one hand. He has an excuse. Okay, so we're going to hopefully rarely use long division because long division stinks. Oh, look, this box right here is called the factor theorem. What it says is a polynomial function f of x has a factor x minus k if and only if f of k equals 0. So basically it says, yo, if you get a remainder of 0 when you plugged in the 0 of that divisor, you found a factor. That's all it says. Look at this box that says fundamental connections. Okay. For a polynomial function and f and a real number k, the following statements all say the same thing. X equals k is a solution or a root of the function f of x equals 0. Yeah. K is a 0 of the function. Yeah. K is an x-intercept of the function. Yes. X minus k is a factor. Yes. You see, all these things say exactly the same thing. That's why every time I've mentioned x-intercept, I've said solution, x-intercept, root, 0, because they all basically mean exactly the same thing. Now, the honest answer to who likes long division was nobody, right? Yeah. So instead, we're going to use synthetic division whenever we can, because long division is time-consuming. Okay, synthetic division. Synthetic division is another way of dividing polynomials, and instead of writing out the entire polynomial, we're only going to be writing the coefficients. See, we don't write the variables. These are just the coefficients. This is like a worked out example for you, showing you how this works. I will say though, that I'm going to do it slightly different than the way the authors did. And that's because I don't really know why they did it the way they did, to be honest with you. Here, right here, and maybe it's a mistake on their part. I'm not sure. I don't know what they meant to show in this picture, but I will show you where I'm going to be doing something slightly different. So stage 1, this is long division. This is what you would see if you did long division. Now look, we got a remainder of 0 at the bottom that tells us that this x minus 3, it tells us that x minus 3 was a factor, right? What that means is if we were to have plugged in x equals 3, we would have got that f of x equals 0. Now, in the next step, what they did is they just stopped writing any of the x variables, or any of the x's. None of the variables are there. So the 2, the negative 3, the negative 5, the negative 12. And the entire long division process also got rid of all of the x's, sticking to only the coefficients. Now, what they were doing here was subtracting straight down. You see that? Remember when we were doing long division, we subtracted straight down, subtracted straight down, subtracted straight down? You guys, you seeing that? Yes? Okay. So that means that you could have collapsed it all vertically into what they've got going over there in stage 3. Here's what I'm going to do, because it was the way that I was taught, and I think that this is strange. I was taught to use synthetic division with the 0 of the divisor. So instead of saying x minus 3, oh, let me do synthetic division with negative 3 and subtract, if you use the 0 of the divisor, you can add. And I think that's easier to do because then you will never run into double negatives and trying to remember what it means to subtract a negative. So if you use the 0 of the divisor, meaning if I had used a positive 3 here, then all of these would have been plus signs instead of minus signs. So it's the exact same work, I just think it's easier. Why our authors chose to go with subtraction, not sure. Maybe they don't like students.
Can I ask, why are we collapsing it exactly?
Because
I don't.
so the reason why we want to collapse, I'm sorry, I'm choking, is because it's faster and easier. We're just legitimately trying to be more efficient with our time, because all of the x's and all that stuff don't need to be there. As it turns out, they follow the coefficients anyway. So if all that matters is the coefficients, why write the x's? That's what we're doing. We're trying to write less, trying to use up less time and less space.
Then just plug in the 3.
Yeah. So
You
for
could
this
just
one,
plug it in
well,
and that
but
would
if you
be
just
like-
plug it in, all that's going to do is tell you what the remainder is. It won't tell you the whole story. It only tells you the remainder. See, the remainder theorem and evaluating by a 0 only gives you the remainder. It doesn't tell you what you would have gotten if you had actually divided. Okay? And we need to know what we would have gotten when we actually divided in order to graph a polynomial. So, like, you plug in a number, woot, you found one of its zeros. That's fantastic, but what about the other ones? And that's why we want to actually see what the what's the thing, not the divisor, not the dividend, what the quotient is. We want to know what that quotient is because we can then continue to factor it or find more of its factors. That way we have the ability to graph it. You'll see, I promise. Let's see, we're dividing 2x to the third minus 3x squared minus 5x minus 12 by x minus 3. And let's see, x to the 3, 2, 1, none. Good. There are no missing terms. We're going to use synthetic division. We're going to write a summary statement in fraction form only because polynomial form is a little confusing. Okie dokie smoky, here we go. And we're going to use synthetic division, not long division, so yay. Like I said, I don't know why our authors chose to use the -3 and then subtract. That's too much work. I would like to use +3 so I can add. Okay, so I'm going to be using the 0 as if I was using the remainder theorem. My coefficients are 2, -3, -5, -12. The very first thing that you're going to have to do, and I said this is going to be a plus, the very first thing that you're going to have to do is just drop this 2 down. You don't have a choice. That always has to come down. This one's always going to have to drop down. 2. There, so that's the setup. This is how synthetic division question will always begin. Now what you're doing is you're multiplying. Remember when we were distributing those numbers we were writing on top of the division bar? We were distributing them to the function or to the divisor. Well, that's what we're doing right here. We're technically, quote unquote, distributing. So we're taking that 3 and we're multiplying it to the 2, and I'm going to erase these lines. You're going 3 times 2 and putting the result here, like that. So it's going to give me a 6. You see that plus sign? Add straight down. -3 plus 6, yep, that's 3. Now again, multiply, put the number right there. 3 times 3 is 9. Add straight down, 4. Multiply.
Was using purple, which is blue, and red mixed together a choice, or was that a coincidence?
No, I just used purple because it looked fun.
So what's a coincidence?
Yeah, it just looked fun. And now 3 times 4 is going to give me the result of 12.
Why does it give you the answer of the part in the top? The first thing at the top.
I'm sorry, what does it give you the answer?
The answer is 2x cubed plus 3x plus 4.
No, it's not. Well, yeah, it didn't give us the answer.
No, up there in stage 1 long division, it's the exact same equation as you get for solving.
Right. No, we were just because they were just showing how to set it up. See, I didn't walk all the way through all the steps of that box up there. I just wanted to show how it works. Also, because I'm using the plus method instead of the minus method, I wanted to show that it still is working. So this negative 12 plus 12 gets us a 0. So here's what we know. We know that x minus 3 is a factor of our f of x. So when you're going to write a fraction form result, you would write it like this. 2x to the third minus 3x squared minus 5x minus 12 divided by x minus 3 is equal to 2x to the second plus, because it's a positive 3, 3x plus 4. Oh, but by the way, x can't be positive 3, because if you plugged in x equals 3, you'd have an asymptote.
Why is the 0 kind of blocked off?
Oh, it's just a thing that mathematicians do. So we blocked off the thing we were dividing by, and we block off the remainder. It's just some things people did.
But
What it shows you is that
yeah.
this is the result. This is the resulting polynomial that I just put in that brace, and the thing afterwards is just the remainder. That's what it's showing you.
Even if it was like a 3, would it still be the remainder?
Yeah, so if it was anything else, let's just say it was a 3, then let's just pretend for a moment it was a 3. It's not, but let's just pretend it was. Let's break math for a momentito and say, uh-oh, there was a 3 here. Then what you would have done, and that didn't mean to be read, but you would have written it like this: plus 3 over x minus 3. That's what you would have done. Okay? Question?
How do you know to put squared?
Good question. How do I know to put a squared instead of a cube? Let me fix my polynomial so it goes back to the way it was supposed to be. Oops, there. The reason why we know it's a square as a result is because we were, in essence, dividing a cubic by a linear.
That's always just one less.
It'll always be, well, okay, I don't want to say it'll always be one less. Could you do synthetic division with a non-linear divisor? You could. I won't, but you could. And so I don't want to say yes, it'll always be one less. It'll always be the degree of the polynomial minus the degree of the divisor. Always. The result. I will not do synthetic division with anything other than linear divisors. The textbook tries to convince me to do otherwise, and I just said, no, screw those guys. I would never do that, so I'm not going to ask my students to. It's not feasible. It's just not. So I think that's a good place to stop for today, because the next thing that we're going to be talking about is rational zeros and Descartes' rule of sign, and oh boy, that deserves its own lesson.
Go over